So today I wanted to get into measures of position. So basically, this is, as the name suggests, we're talking about this where in the data set are your numbers, placed. So what their position is in your data set. And so for the measures of position, we can talk about standard scores. They are also known as z-scores. We have percentiles, deciles, and quartiles, which are actually like percentiles. It just depends on how many parts we're breaking them up into. I would imagine some of you should at least be familiar with the term of a percentile. Does anybody know what a percentile is? Or where you have heard it being used? So if you've ever taken like SAT, ACT tests, if you look at your scorecards, they always tell you what percentile your score is falling into. I know when my friend had her son, especially those first couple years, every time she took her son to, yeah, Sabri, that's what I was gonna say. Every time she took her son to the pediatrician, they would always tell her where his growth rate was. So he was always in his height, he was always like in the 95th, 96th percentile, but for his weight he was always on the lower end. I think somewhere in the 80s, because he is a very skinny tall kid. Both his parents are like 6 feet 2 inches tall, so you can imagine he's a tall kid but hardly has any weight on him. So he would always score high on the height chart, but not so much in the weight. He was never underweight, but just for somebody as tall as he was, he just didn't have enough weight on him. So a lot of times that's where they use percentiles. So like I said, your standardized test scores, SAT, ACT, those kind of scores. So the standard score, as I said, sometimes is also called as a z-score. This one is actually used to see from the mean how far away are you. So you can see in this calculation, we use the mean and the standard deviation, and we'll actually come back and do this exact same calculation when we talk about normal distribution. And I think, is that chapters 5 and 6 or 7 and 8? One of those chapters. With the new textbook, I'm a little confused about my chapter numbers. But basically, like I said, when we talk about normal distribution, we will be talking about the z-score again. So basically, the idea is how far away from the mean is our z-score going to be, in terms of standard deviation. So this calculation, as you can see, depending on are you using the sample or a population, the symbols change a little bit. You're using mu and sigma for the mean and standard deviation for population, or X bar with the small letter S for mean and standard deviation if you're working with samples. So this one over here is a nice, neat example. You can see they're talking about a standard score of 85 on an English test. So a student scored 85 on an English test, whereas the mean score for all the students was 76 and the standard deviation was 4. So this was in the English test. We're saying the same student scored a 42 on her French test, where the class mean was 36 and the standard deviation was 3. So you can see, these two exams are based on a different grading scale or different overall scores, because you can see this student has a score of 85 when the mean was 76 for the English class, and then she has a 42 when the mean was 36 in the French class. So which exam, I guess you want to know, maybe relatively she did better on. So they want to talk about the relative position. So using our z-scores for the English test, you can see we take her score of 85 minus the class mean divided by the standard deviation, and you can see her z-score is coming out to be 2.25. For the French test, her score was 42, the class mean was 36, and the standard deviation was 3. So you can see she scored 2.00 on the z-score. So this actually tells you that her score in her English class was a little bit higher than her score in the French class if you compare it to, the entire class, all the students who took this exam, because the farther away you are from the mean, that means the higher score you have. The closer you are to the mean, that means, with respect to the other class members, she didn't do as well. So the 2.25 and the 2.0 is actually talking about your bell curve. And I'm actually going to show you, we had done the empirical rule in this section over here. So basically, if you think about this as our bell curve, your mean is always going to be in the center. And then you are 1 standard deviation away from the mean, and you are 2 standard deviations away from the mean. So remember how we had talked about with standard deviations that we were talking about on an average, what is your distance away from the mean? So the standard deviation is again a calculation of the average, but it's looking at the distance from the mean. So on her French exam where she has a z-score of 2.0, that actually means she is 2 standard deviations above the mean. So that's where her score falls, 2 standard deviations away from the mean. But on her English test, she got a 2.25. So that means she is slightly higher than 2 standard deviations from her mean. So this is telling you that she is at 2.25, so 2.25 standard deviations away from the mean, because your z-score is a measure of position. So it's just telling you, with respect to the mean, how many standard deviations above or below the mean you are going to be. And like I said, this is the same discussion we will be having, but we'll get a little bit more in depth with normal distribution. So here we're just introducing this idea of how far away from the mean you are, using the z-score as a sense of calculation to find that position where you are at. So you can see on 2 things that really are not quite on the same scale, by using the z-scores, we can still find what their relative position is, and that gives us an idea of our standing. And you can see a couple different examples over here. This one is talking about the age at which people are getting married, I think. So this one says mean age at which men are getting married is at 26.4. The standard deviation is, about a difference of 2 years. For women, the mean age is 23.5 and a standard deviation of 2.3. So for a gentleman who marries at the age of 24 and a woman who marries at age of 22, what kind of relative position are we looking at? So you can see with the men calculation, since the mean was at 26.4 and this person is at the age of 24, since this is a number less than the mean, you will get a z-score of a negative number, because the negative number tells us you are below the mean. So this person was at negative 1.2, so he is just slightly less than 1 standard deviation below the mean. And then for the woman, you can see they're saying the lady got married at the age of 22. The mean age for them is 23.5. So once you do this calculation, again, you'll see 22 is a number smaller than 23.5. So again, you are going to get a negative answer. So that means her position is relatively at negative 0.65. So more than halfway, but still less than 1. So, somewhere over here, negative 0.65 is where the woman's age who marries at 22 falls. So you can see they're saying the woman's age at marriage is relatively higher than the man's age at marriage, because, of course, he has a smaller standard deviation than the woman had. So with the respect to just women, she is at a relatively higher age when you compare it to the man who gets married at 24. So even though, if you just talk about, well, she's only 22 and he's 24, he's 2 years older than her. But when you look at the z-score, that of course tells you her z-score is closer to the mean than his. So that's why she is, relatively higher at her age than he is. So that's kind of how you use the z-score to help you with these measures of position. And then, like I said, the other calculations we have are percentiles, quartiles, deciles, which are pretty much the same thing, just depending on how many equal parts we break up our values in. So they are saying if you take a data set and divide it into 100 equal groups, that's where we get percentiles. Now, one thing I will tell you guys to be cautious about, please do not confuse percentages with percentiles. Two very, very different things. Even though they sound similar, the idea is percentages are also broken up into 100 equal parts. They are not the same calculation. The percentage is basically, like your relative frequency calculation. Percentile is the position. Where are you positioned in the data set? So you can see they're talking about, you can use these symbols, P sub 1, P sub 2, P sub 99 to denote, which percentile you are looking at. But basically the idea is, you can kind of go through and look through some of these explanations over here. They're talking about, the growth of a person and that kind of thing, just different examples. But this one over here, you can see the systolic blood pressure example, and they kind of go through, completing our distribution table using cumulative frequency and cumulative percentages, and they actually come up with this percentile graph over here. So you can kind of look through, and percentile graphs are definitely something that's used. If you look at these growth charts and that kind of things, you will see that they will always have this percentile graph to kind of describe it. And all that basically says is, in this case, if a person has a blood pressure of, looks like 130. So, if their blood pressure falls somewhere in that 130 category, that means they are in the 70th percentile for, these blood pressures. So what that means is, out of all the people whose blood pressures have been recorded, 70% of them will have a score below 130. So their blood pressure will be below 130. So that's what I'm saying. Percentages are not the same as percentiles. Same thing over here. I think this number, what does that represent? 118. So they are saying if you have a blood pressure of 118, then this person will fall in the 40th percentile. So which means out of all the people whose blood pressures have been recorded, only 40% of them have a blood pressure lower than 118, which is kind of scary. You would imagine people should be more in the normal range than on the higher one. So your percentile calculations are based on how many, whatever data value you are looking at, you're talking about how many values are below that data value, add a 0.5 to it, divide by the total number of values, and then you multiply it by 100, because we do not want to leave our answer in decimals. We do want them to be whole numbers. So just to show you how that calculation works, they have a number of traffic violations here recorded over a 10-day period. So how many traffic violations happened on a given day? You start by putting them in order, and this is important because we want to know, how many data values are below. So put your data in order, and then they're talking about, okay, so we want to know the percentile value for number 16. So they're saying find the percentile rank of 16. So you can see over here, once we put it in order, here's our 16. There are 3 data values that fall below 16. So you can see that's where the 3 is coming from, the number of values below 16. We add a 0.5 to that. There's a total of 10 data values over here. So divide by 10 and then multiply it by 100. So that falls into the 35th percentile. So we are saying the values of 16 is going to be higher than 35% of the data values, which means below 16 is 35% of your data value. So again, it's just giving you where exactly in your data set the 16 falls. You can see another example over here, just a percentile rank of 24. So you can see right here is 24, which is in the 9th position. So that means we have 8 data values below it. So that will be 8 plus 0.5 divided by 10. And then again, multiply by 100 to change it to a whole number. And this number will fall into 85th percentile, which means 85% of our data values fall below 24. Or in other words, they're saying data value 24 is higher than 85% of all the data values that you have in the set. So they're just kind of giving you the idea of how to calculate your percentile. This is an interesting little procedure table over here. If it tells you if your data value that you are looking at, if it's a whole number or not a whole number, what you should be doing. So you can kind of look through some of these examples to get an idea of that. So when you're talking about quartiles and deciles, same exact concept. The only difference is with quartiles, we're breaking it up into 4 equal groups. So instead of breaking it up into 100 equal groups, we break it up into 4 equal groups. So you've got quartile 1, quartile 2, and quartile 3. So you can see below quartile 1 is 25% of your data. Below quartile 2 is 50% of your data, and below quartile 3 is 75% of your data. So this goes in, think about quarters, right? 25%, 50%, 75%, and then you're at, 100% limit for that last quarter. So quartiles are when you break it up into 4 equal parts, your data set into 4 equal parts. And again, they kind of walk you through the procedure over here. So as you can imagine, your deciles is when you break your data set into 10 equal groups. So you can see you're basically breaking it up into groupings of 10% each. So you have your decile 1, decile 2, decile 3, and each one of those, will have 10% below it, 20% below it, 30% below it, depending on where you are going to be. So that's kind of how the percentile, decile, and quartile calculations work. Now, this is something very interesting. We talk about the interquartile range. So we're basically saying if you take the difference between quartile 3 and quartile 1, it will tell you, what percentage of your data is going to fall in that middle, which, as you can imagine, if we're taking the difference between quartile 1 and quartile 3, that's going to be from here to here. And that's going to be 25 plus 25, 50% of your, middle data values. And that's what they're talking about here. The measure of variability, which uses quartiles, is called the interquartile range. And in the range is the middle 50% of your data values. And this calculation we're actually going to need when we talk about box plots. So before I get into box plots, very quickly, I wanted to talk about one other terminology that we have not used yet is what is an outlier. An outlier is where your data set has an extremely high or an extremely low value compared to the rest of your data set. So you either have a really large value in your data set or a really low one. And what that does is actually change, especially when we talk about our mean, median, mode, mid-range calculations. They can make a big difference, because think about it, and you can see this example here. You've got these numbers going from 5 to 22, and you can see they're still relatively close to each other, but then you have a really high number, 50 over here, and look at the big gap between 22 and 50. So they actually go through a process of how you can identify if your data set has an outlier or not. So they start out by, putting your data set in order from smallest to largest, finding your quartile 1 and quartile 3, calculate the interquartile range, multiply your interquartile range by 1.5, And then they're talking about subtracting this value from your Q1 and adding it to Q3, quartile 1 and quartile 3. And then you have to do this very little comparison at the end to see if all your data values fall within this range or if it's going to be outside it. If it's outside it, then we say it's an outlier. So in this case, number 50 is definitely an outlier. I don't know if that example is in a different section, but there's one example in your handout which talks about 5 employees at a company. 3 of them make like somewhere near 40,000. I think the manager makes like 60 or 80,000, but the owner of the company makes like 150 or something. So you can imagine 4 of those employees are staying within the 40 to 60 or 80 range, but then you have the owner making like a 6-figure salary. So again, if you can imagine, his salary is going to be considered an outlier. And outliers, guys, have a big effect when you calculate your mean, because think about the mean. You add all the numbers, divide by the total. So if you have a really large number in there, it's going to pull your mean towards that larger number. Mode does not get affected by the outlier unless your mode is going to be the outlier if it's being repeated many times, but that usually does not happen. The median does not get affected by your outlier because median, again, you're trying to find the position in the center. So if the number is really small or really large, then the outlier does not affect your median. Mid-range can be affected by the outliers because remember, mid-range is where you take the lowest data value and the largest data value, add them together and divide by 2. So the mean and the mid-range are going to be the 2 calculations that definitely get affected by the outliers. And so you can imagine if you have a really large number or a really small one. So if everything is in the hundreds, but then you have a number which is in the 20, then that's going to have an effect on same thing, mean and mid-range also. So outliers are definitely something we have to watch out for as you're going through these measures of position. It really does make a difference of where your data value is going to fall. So let's actually look at how we can use these ideas of quartiles, the interquartile range, when we come up with this 5-number summary and box plot. So what we do for the 5-number summary is we actually find out what is the lowest data value in our data set. So, that's going to be the most smallest minimum value. We find out what our quartile 1 is going to be. Find out our median, which is also known as quartile 2, and then find out your quartile 3. So we use those 3 quartile calculations. And then we also need to find out what our highest value in the data set going to be, and that's going to be our maximum. So these 5 numbers, make up your 5-number summary, and these are the same 5 numbers we use to draw a box plot. So if you look at this example over here, we're talking about the number of meteorites found in 10 states. So you can see what these numbers are. The first thing we're going to do is arrange them in order. So going from smallest to the largest. So of course, you can see this guy is going to be our minimum. This guy is going to be our maximum value. Now to find your quartiles, this is what you do. If you have an even number of data set like this guy does, the first thing you're going to do after you put it in order is find out where your median is going to be. So you have 5 values below, 5 values above. So that means you're going to take the centermost 2 numbers, add them together, divide by 2, and that's going to be our median, which is also known as quartile 2, because remember, this is the guy that falls right here in the middle. So here's your median or your quartile 2. Once you have calculated the quartile 2, then you take each one of these 5 numbers on either side, and then you find their centermost position. So we take our first 5 numbers, 30 to 78, and you can see them right over here. And the middlemost position is going to be 47, which is our quartile 1. Then you take the numbers from 89 to 296, which is the second 5. Find the centermost position, which is 164, and that's your quartile 3. So literally you are finding the median for the entire data set, and then you take the bottom half and find its median again, which is the quartile 1. You take the top half, find its median again, and that's your quartile 3. So that's how we come up with the 3 quartile values. And then basically what they have done is, created a horizontal axis going from the smallest number of 30 to the largest number of 296. So you can see that's why they build this on a scale going from 0 to 300. Our lowest data value is 30. So they're kind of, positioning it where you think 30 would fall on this horizontal axis. Our largest number was 296, so going to be somewhere here closer to 300. My quartile 1 was 47, so you can see this is kind of where they're putting that 47. Quartile 3 was 164, and then our quartile 2, or the median, was at 83.5. So using these 3 numbers, guys, this is also called as, oh, that name just went out of my head. Whiskers something. Oh, a box and whisker plot. So you've got your box in the middle, and the whiskers are the 2 horizontal lines at the end. So we start from quartile 1 to quartile 3 is where we create this little box where you have your median. You put that horizontal line in the middle. So that creates our box from quartile 1 to quartile 3. And then from there to your minimum and the maximum value, you create these, whiskers, the horizontal line. So that's the idea of creating your box plot. And what your box plot does, remember, this is about position. It is telling you how spread your data is. So depending on how, long those lines at the either end are going to be, gives you the idea of how spread out your data is. But then the little box in the middle kind of tells you, where your data values are kind of concentrated, where your, interquartile ranges. And remember, the interquartile range is taking quartile 3 and subtracting quartile 1 from it. So 164 minus 47 will give you the interquartile range, whatever that number comes out to be, 100 something. And now you can see with the median being right over here at 83.5. Yeah, Lise, I thought something like that must have happened. I'm glad you were able to join back in. So what this actually tells you is, where is your median falling? And you can see your median is still kind of towards that lower end, right? Because it's below the 100. So you can use this to kind of talk about the shape of your distribution, what kind of symmetry or no symmetry you have. So you can see they're saying if the median is near the center of the box, then we can say our distribution is approximately symmetric. Well, our median is definitely not in the center, so we know this is not symmetric. They're saying if the median falls to the left of the center, then your data is positively skewed, which means, remember, your taller bars are going to be on the left-hand side. And then as you move to the right, it gets, smaller and more flatter. So that's your positively skewed. They are saying if the median falls to the right of the center, so, the right of your box, then that means your data is negatively skewed. So this is coming from just looking at the box in the middle and where that line for the median falls. Now, looking at the whiskers, the 2 horizontal lines, they're saying if the 2 lines are, again, approximately the same length, then we can say our data is approximately symmetric. If the right line is larger than the left, our data is positively skewed. If the left line is larger than the right, it's negatively skewed. So of course you can see with ours, the data is positively skewed because we have a longer right-hand side line. Additionally, my median was towards the left. So again, that means my data is concentrated on the left, and it starts tapering down as we go to the right. So that's kind of how you can use these box and whisker plots, or box plots, to kind of help you just get a simple idea of what your distribution looks like. But then also, you can kind of see, just by using these calculations for our position, we can get a decent idea. So what happens here, guys, you don't have to create a histogram, you don't have to create a frequency distribution table. This can give you that general idea of what the shape of your distribution is going to look like. But of course, if you want more detailed values, then that's where we get into creating our frequency distributions, creating our histograms, looking at what kind of distribution we have. So you can kind of think of, box plots helping us out with that initial part of what kind of shape we have. So they've got different examples in here. You can do comparisons between two different categories. So here, they're talking about comparing wooden roller coasters to steel roller coasters. So they've got, I believe this is based on speed. Yeah, the speed in miles per hour for a sample of wooden and a sample of steel roller coaster. So you can see with our wooden coasters over here, once we do our calculations, what your median quartile 1 and quartile 3 end up looking like. Remember, your median is same as quartile 2. They're doing this for the steel roller coasters as well. And then once you have your 5-number summary, this will be the lowest and the highest, lowest and the highest. We can go ahead and draw our two box plots on the same horizontal line, or the same horizontal axis. And now you can kind of see, of course, the wooden roller coasters have a slower speed compared to the steel ones. And that's just because, of the construction material that's used in them. You cannot go too fast with the wooden ones like you can with the steel roller coasters. And then you can kind of see what the distribution here looks like. So even though your median is kind of falling right in the center of your box, you can see our left line is just a little bit longer than our right one. So this is almost kind of being symmetric to maybe a little hint of negatively skewed. But then when you look at the steel roller coasters, of course, our median is a little bit more towards the right-hand side of the center of our box. And then you will also see the left-hand line is a little bit longer than the right-hand one. So this one is definitely more negatively skewed. If you talk about the shape of the steel roller coaster, just the shape of that. So you can kind of see a little bit of that from here. And just comparing the two types of roller coasters, obviously you can see if you were going for speed, you want to ride a steel one as opposed to a wooden one. So just how you can combine, more comparison values within one box plot. So just some examples to kind of help you look at how we can use some of these position calculations to help us find out, what our data set looks like. So this was using quartiles, but then remember how we were talking about we can use percentiles to kind of keep track of, what the position of your data value is within its own data set. So that's where a lot of times we use percentiles. We don't really do quartiles and deciles on that one. Dennis, what was your question about?
So on these boxes down here at the bottom, can we interpret the box itself? So let's take these steel versus wooden roller coasters boxes here real quick. So the top would be a curve from 35 to 72 with a very narrow, tall peaked curve from 49 to 67.5. Versus the bottom would be a much more shallower curve.
So it's not going to be so much as a curve because remember, again, this is just the idea of, if you were going to put this on a histogram, And I'm trying to think what the histogram would look
So what
like.
I'm saying is the width of the curve would be, super steep like this on the top one versus more like this on the bottom one, determined by the inside box, where the center line would shift it side to side in the overall range.
Mm-hmm.
The center box shifts in the range, but the shape of the curve going a steep bell curve versus a shallow bell curve.
See, and that's
They
what I'm,
create that type of histogram, I guess. Is
because
the
this
question.
will not have a bell curve. This will, because bell curve is implying symmetry, and this one is somewhat symmetric, but you do have, so you will have a little bit of that symmetry, but you will have a little bit of a longer tail over here. Because you can see how the left-hand line was a little bit longer. So that's telling you you have just a little bit of that tail coming through over here. Whereas with the steel roller coasters, if you had to do a curve, then you would have the higher part on the right-hand side, but then more of a tail, going on the left. So yeah, the wooden roller coasters will be somewhat symmetric, but just a little hint of that, negative skewed because of that longer whisker on the left-hand side. But the
Okay.
steel roller coaster is definitely negatively skewed.
Okay, yes, they're both negatively skewed, but the two diagrams you just drew,
Uh-huh.
the bottom one is the curve I would get the impression that the top one makes versus the top one being a wider bell, where the bottom is a wider box. The top box is a narrower box. Yes, they're both skewed on the line, shows the skew right or left, or positive, negative, I guess,
Right.
where the size of the box shows kind of the shape of the bell.
Yeah, so it's just because it would just tell you you have more of your data values that fall in the middle. And this one, of course, you can see there were not that many numbers to show you a variation quite as much. And so, yeah, you can kind of think of I guess, the curvy part of your distribution being narrow or wider. Yeah. So this was just to kind of emphasize, the bottom graph that I drew was to emphasize that you have a longer tail over here and the one on the top does not. So I'm really not focusing on the width of the curve itself. This was just to show you that the bottom one will have a little bit more of a longer tail on the left-hand side. Okay, very nice. Did anybody else have a question on that? So again, guys, remember that percentiles are probably one of the more common calculations used, when we're talking about the measure of position. And then with the other one we had looked at was the z-scores, which we will be revisiting when we get into our normal distribution calculation, because that is where you literally start the normal distribution calculation by using, these formulas over here. So measures of central tendency, measures of dispersion, and measures of position are probably going to be the biggest things that you want to take away from this chapter over here. And then remember, we had talked a little bit about our empirical rule over here. And I again want to emphasize, this is again going to be something we will talk about again in that chapter where we talk about normal distribution, because you will see we'll come back and revisit these percentages where we are talking about, and let's clean this up a little bit over here. Will it let me delete that? Okay, there we go. So when we're talking about these percentages, we're basically saying all the data values that fall from the first standard deviation below the mean to the first standard deviation above the mean. So all of these data values make up 68% of your total data. So 68% of our data value is going to be contained within the one standard deviation below and one standard deviation above the mean. So if you look at this example over here, they're saying the scores on a national achievement exam have a mean of 480. So that means your mean of 480 is what's right here in the center. So that's the mean of 480 here. We're saying you have a standard deviation of 90. So if you add 480 plus 90, that brings you to 570. So this would be the score of 570 over here. Mean is 480. And if we take our mean and subtract 90 from it, we get 390. So basically we are saying anybody on this national achievement exam who scores between 390 and 570, they are going to make 68% of the population who has taken this exam. Then we are saying if you go 2 standard deviations above the mean and below the mean, so that would be everybody from 2 standard deviations above the mean and below the mean. So, of course, that would contain that 68% group also. And that score, it looks like is coming out to be our mean plus 2 times the standard deviation gives you 660. So that would be right here. And then our mean minus 2 times 90 will come out to be 300, which is going to be here. So anybody who scores between 300 and 660 on this exam, they are going to add up to 95% of the data value. So imagine everybody who's taken this national achievement exam, 95% of the people will have scored between 300 and 660. And in that same way, they're saying if you go 3 standard deviations above the mean, so 3 times 90 plus the 480 will put us at 750 here. And then 3 times 90 minus 480, so 3 standard deviations below the mean, you're at 210. So everybody from the score of 210 all the way to the upper score of 750. And where's my 750? There it is. So everybody from here till the 210 over here, all of these are making 99.7 of our entire data set. And that's again the people who took this national achievement exam. So imagine 99.7, just 0.3% shy of being 100%. So 99.7% of the people are falling right over here in this little center part over here. So imagine these little tails that we have left, they add up to 0.13, which means this little tail here is 0.15%. And this little tail over here is 0.15%. So together, all of these, make up your 100% of the data set. So this is the same breakdown we talk about in normal distribution. So literally what they're doing is introducing the concept of this normal distribution, or you can call it the bell-shaped distribution. And then over here in the position section, they're introducing you to z-score, because the z-score tells you, where you fall in terms of your mean, how far above or below the mean you are. Okay, Haley, that's fine. If you got to leave, I'll see you at the next class, okay? So just remember, guys, we will be revisiting this more formally when we talk about normal distribution, but that's exactly what you are doing over here, is discussing these normal distributions. Now, one thing you have to be careful about, and I told you this last time, they have to let you know if your distribution is bell-shaped or if it's normal for us to be able to use these, percentages, these calculations. If they don't say anything about the shape of the distribution, then you cannot assume it's bell-shaped. And that is when you have to use this Chebyshev's theorem to come up with the calculations. So you have to use, this, I guess I want to call it a formula, the 1 minus 1 over k square, to figure out, what kind of percentage you are looking at. So what this basically says is if you are 2 standard deviations below the mean and 2 standard deviations above the mean, then we can safely say that 75% of your data is going to fall within this range. So you've got 75% of the data right here between 2 standard deviations above and below. With 3 standard deviations, you get into, almost 89% of your data. So we're saying, from here, everything in the middle to here is 89% of your data. So you can still see, at the ends, then you will have approximately 11% remaining. And this can be applied to any shape of distribution. So you can see this one here is positively skewed. You can use this on negatively skewed, uniform, or whatever the distribution will be. You can use Chebyshev's. But if they specifically tell you that it is normal distribution or your distribution is bell-shaped, then remember, this is the distribution you are looking at, the 68, 95, 99.7% of your data falling between that 1, 2, or 3 standard deviations. Let's see. Any questions about what we just talked about? Measures of position and the 2 distributions. Nothing coming to mind? Okay. So again, just wanted to remind you guys that you are turning in the precedence ages. Oops, sorry. Assignment on Wednesday by midnight. So remember, you have, and we talked about this last time, so you have your ages given to over here. You can go to random.org to help you come up with those 10 samples of 10 numbers that we talked about. You have your template given to you over here. So this is where you'll enter all your information. So the first page of the template is going to be the raw data file, but just click on that second sheet at the bottom where it says template, and this is where you will find the blank spaces where you will be entering all your information. And then remember, guys, you are also going to be making a video recording of your findings, and you have a link here for the Flipgrid website, so you will be submitting your recordings over here. So just please make sure, don't wait till the last minute. I would say try to work on this today or tomorrow, so that way if you have any questions, you still have time to ask me. If you wait till Wednesday evening to work on this and then ask me questions, I will not be available. So please do not wait till the very end to submit this in. You will be able to copy the template or download it as an Excel file, so you will not be able to work directly in here. You will need to either make a copy or download it as an Excel file. So just make sure you take care of that. And then Wednesday in class, we will be taking our chapter 3 exam. So you can see, again, like we always do, your homework assignments will close at 1:45 p.m. right before our 092 class. So just make sure you have all of your homework completed with a minimum of 90% grade. You have a quiz for chapter 3, and then, of course, we'll take the exam in class. So as always, I'll give you your password, you'll take the exam in class. And then when you're done, you will be welcome to leave. We wouldn't have to stay. Anybody have any questions about the US president's ages example? So please make sure you're not coming up with your own numbers. Use the random.org random number generator to help you come up with, that part where you have to create this, because this is the part I'm really worried about. You have to get the right calculation. So you have to randomly select 10 ages, from all of these 45 ages that are listed over here. So just think about, each one of these ages being listed from, 1 through 45. So in the random number generator, if you come up with number 20, so remember that means you're looking at the age, which is in the 20th position. If your random number generator from 1 to 45 gives you 37, then remember you are looking at the 37th age in your set over here, which will be this number 56 over here. So basically use the random number generator so you have no control over what numbers you come up with, and you can select the, age related to that number. That's all I can think about as far as this assignment goes. And then, chapter 3, I have only 4 handouts because your textbook has actually broken them up into multiple sections. So even though it's the 5 sections, it's still the same material that we talk about in our handouts. And again, if you guys have had a chance to read through the textbook, then you will be familiar with what all the content is. So no questions on chapter 3? Okay, so how about we look at our next chapter over here, then, if you guys don't have question on chapter 3. Give me 1 second over here, okay?